open communication is really about being willing to tell the unvarnished truth, especially to your management. And they taught us you don't stop until you go to the chairman of the board if you think that a decision is wrong. Those core values and the way in which they were implemented, single most important reason for the turnaround of Lam Research, which was 1 quarter from bankruptcy in 1998, and today I think is approaching $400 billion in market cap. If you didn't have plasma etching along with lithography, the cell phones that we all have in our pockets today would be as big as a big suitcase. As CTO, my mission is to create new business opportunities that get measured in billions, not millions. Moore's Law, it's not dying, it's just changing. It's a lot more interesting and challenging now, and I've already seen some innovative ideas that will be very disruptive in that space.
Welcome to Deep Tech Live by SOSV, the podcast where we explore the frontiers of deep tech and its impact on our world, with the help of top technologists, researchers, and pioneering founders shaping tomorrow. SOSV Deep Tech Live.
Welcome to SOSV and Deep Tech Live. I'm Susan. I'm a partner at SOSV, and I'm also Chief Science Officer for HACS, our hard tech program. It's my absolute pleasure tonight to be here with Dr. Rick Gottscho. He's the retired head of products and CTO, ex-CTO of Lam Research. Welcome, Rick. Thanks for being here.
Thank you, Susan. It's a pleasure to be here.
So I want to start by asking you a little bit about your own history. Ultimately, you ended up studying chemistry, which I also am a PhD in chemistry. So would love to understand your history. How did you get into chemistry, and kind of how did you get onto the path that you ended up on in your career?
It's a little bit of a long story, but I'll try and keep it short. Started in 5th grade or 4th grade when I discovered the periodic table. And I just thought that was one of the most beautiful things. I from the earliest age, I always questioned why we're here, what life is about, what's the meaning of life. And I don't think the periodic table quite answered all those questions, but it went a long way towards it. And my father was a chemical engineer, so I was exposed to chemistry and chemical engineering. And I took advanced chemistry classes in high school, and then I went to college at Penn State. And in my freshman year, I didn't declare anything. My father said, you should go to the College of Liberal Arts because you'll get a liberal education. And he didn't realize that the College of Science and the College of Liberal Arts were very distinct, separate admission procedures and so forth. So I went into the College of Liberal Arts, and I took a class in social psychology, which I thought was really, really cool, because I pretty much decided I want to be a scientist, and they were doing experiments on people. I think a lot of those experiments have since been discredited, but I thought it was pretty interesting what they put people in really literally torturous situations and see what they would do. And so I declared my major as sociology, thinking I'd do social psychology experimentation. And then I started my sophomore year, and I found myself in the most boring classes I could imagine, not scientific, and with all due respect to a man named Piaget, who wrote a treatise on raising children, which struck me as nothing but maybe well-informed opinion. And so I became a little disgruntled. I had a roommate who was a big science fiction fan, introduced me to Isaac Asimov, and an article that Isaac Asimov wrote called Science Fiction, the Only Relevant Literature. And I thought, and that article was very compelling for me. And I decided pretty much as soon as I finished reading that article that I wanted to become a physical scientist so I could learn more science and write really good science fiction. And I like to tell people I've been writing science fiction probably most of my career, although people don't acknowledge it as science fiction. So I went to my advisor and said, I want to switch to the Department of Chemistry in the College of Science. And they looked at me like I was crazy because everybody was going the other way. So they accepted me. I had exempted freshman chemistry and I was more interested in physics actually than chemistry. So I became a physical chemist. And there's a joke about physical chemists. If they run into a physicist, they talk about chemistry. If they run into a chemist, they talk about physics. If they run into another physical chemist, they talk about baseball. So I got involved in some undergraduate research doing laser spectroscopy most of my experiments didn't work. And then I went on to MIT and I got involved in molecular spectroscopy, atomic spectroscopy. And so when it came time to look for a job, I had been collaborating with some people from Bell Laboratories. That kind of gave me an in for an interview. And I went there, and the director of the Materials Research Laboratory, I don't remember the exact name, guy named Bob Lodis, who was a crystal grower, if I remember correctly, introduced me to plasma etching. He asked me, do you know anything about plasmas? No. You know anything about etching or making semiconductors? No. Well, we think you're the right guy because these things emit a lot of light. There's a lot of very reactive species, and we think laser spectroscopy, molecular spectroscopy, atomic spectroscopy are a great tool to study these things. And they're really important because we just put it into manufacturing to etch fine features in the fabrication of integrated circuits. And it works beautifully, but nobody really understands why it works. There are big debates. So we need to understand it better. And that's how I got into semiconductors and plasma chemistry and plasma physics from my molecular spectroscopy background. That was 1980. Let me pause.
Okay, so a bit of foreshadowing here for how important plasma is, of course, in the semiconductor industry. So at some point you left Bell Labs and went and joined Lam. And I want to ask, what was the state of the semiconductor industry at that time? Where was Moore's Law? Sort of give us the state of the art at that moment.
Well, a little bit more about Bell Labs, because I think it was in 4th or 5th grade when I first heard about Bell Labs and the Davison-Germer experiment. And I always wanted to go to Bell Labs. So it was like a dream come true for me. But and at the time I joined Bell Labs, everybody was running around the hallways saying Moore's Law is going to end because we can't go below 1 micron technology. Optical lithography will never work below 1 micron. It's a really important thing to keep in mind. 1980, people were talking about the end of Moore's Law, and I don't believe it any more today than I did then. But so I worked on a lot of different projects at Bell Labs with the guys in silicon, the guys in Lightwave. But eventually, I honestly lost confidence in AT&T Corporation, not Bell Labs. And it was at the time when AT&T had been broken up in 1984 by the federal government, and again was splitting itself up in 1995, spinning off NCR, that they made a hostile takeover for $7 billion. It was a failed enterprise, and they were going to split the company into long distance and manufacturing. So I decided I was maybe going to have to change my job or lose my job. I was going to do it on my terms. I knew a bunch of people at Lam Research. I was enamored with their technology. They had something called transformer-coupled plasma, which was a novel way of doing plasma etching. And so that's how I ended up at Lam. At that time, the technology was quarter micron, 250 nanometers, was being developed. That was 15 years after I joined Bell Labs, so 15 years to go from 1 micron to quarter micron as an industry. The industry was in terrible shape. Lam actually turned out to be in pretty bad shape, which I didn't realize until after I was there. The semiconductor industry is very cyclical. It was more cyclical back then because you had many companies, hundreds of companies making semiconductors, and you had a few more equipment companies. And so everybody's trying to grab market share. So everybody's investing and buying all this equipment. And there's a long lead time to get the equipment, 6 to 12 months back then. And so by the time the capacity comes up, now you have an oversupply situation, and the chip makers can ratchet back their production such that, they're at least covering their running costs, their variable costs. Fixed costs are what they are. And so what they do is they just stop buying equipment completely because they don't need any more equipment. So when the cycles hit, everybody suffers, but the analogy I like to use is the equipment companies are like the flea on the tail of the dog. And when the dog gets excited, the flea goes for a really wild ride. And that's the way it was for the equipment companies. So there was like no sales, no business. the company was overextended. Its growth strategy was to try and diversify. It started as a pure etch company. And the vision of the founder, David Lamb, was really brilliant. He just focused on reproducibility, minimum variability, high reliability equipment, processing one wafer at a time. But he was pushed out after a couple of years, and the leader of the company wanted to grow the company by going into different markets, and they weren't too discriminating in technologies that they acquired, and they spread themselves too thin. So when the downturn hit, they were in a lot of trouble. 1998, we were one quarter away from bankruptcy.
Wow.
So that's what I walked into.
So maybe just to interject here, just to share with everyone plasma and sort of why it was important, why it was called upon at this time or in general, right? For many years, I think when I ask you the question of plasma, why now? I think your answer is plasma always, right? Is always important. But tell us a bit about specifically why plasma is so important, especially in this industry.
Well, back in the 70s, the way chips are made is you basically do a photographic process, photolithography, and print a pattern of your circuit into a photosensitive material called photoresist. It's called resist because it resists etching. And so you take that pattern, you project a pattern into the photoresist, you develop it, and then after you develop it, you transfer it into the underlying materials via etching. And all the etching was done back then using wet chemistries. Problem with wet chemistries, with some notable exceptions, is they etch isotropically. In other words, they etch in this direction at an equal rate to that direction. So if you're trying to increase the density of transistors on your chip, and you're trying to create features that are smaller and closer together, if you use wet etching, you just undercut the mask and you lose the entire pattern. And what was discovered serendipitously is that if you put this pattern into a reactive plasma, and back for etching silicon, it was typically carbon tetrafluoride mixed with a little oxygen, for example, to make free fluorine, which etched the silicon, and you get a little deposit on the sidewall to give you a little passivation, it would etch vertically. It wouldn't etch laterally, ideally. And so that allowed you to cram things closer and closer together. There's a beautiful review article written, I think, around 2010 by Avi Kornblit and Vince Donnelly, who were at Bell Labs at the time. And they likened it to, if you didn't have plasma etching along with lithography, the cell phones that we all have in our pockets today would be as big as a big suitcase, and you'd need it on wheels to carry it around because it would be so heavy. So it's not all about lithography. It's really about lithography and etching that drives this constant increase in density and exponential growth in the cost per bit. And that's the real value of plasma etching.
So selectivity, really, and being able to do this small feature size.
You have to do it selectively, but wet etching is really good for selective etching. Actually, plasma is not as good as wet etching as far as selectivity is concerned. It was all about anisotropy.
Directionality. Yep. Okay, so coming back to Lamb then, you joined and then they were a quarter away from bankruptcy. But can you talk a little bit about what happened and how the company turned itself around?
What happened was the board of directors realized the company was going in the wrong direction, and they engineered the acquisition of a small company called OnTrack that was doing chemical mechanical polishing, which was a move in the wrong direction because now we got another product line that's not well established and diluting resources and making the people working on etch even more miserable. But there was a CEO of OnTrack named Jim Bagley, who started his career at Texas Instruments. And back in the 60s and 70s, everybody making chips also made their own equipment because there was no equipment industry. They had no choice. And he led the equipment division for Texas Instruments. He got hired away by Applied Materials in the early 1980s and helped to build Applied Materials into the largest process equipment company that they are today. ASML is the largest equipment company because of their lithography position. And he was an electrical engineer, but he was also very, very strong operationally. He rose to vice chairman of Applied Materials, but ended up having some disagreements and decided to leave and became CEO of OnTrack. Lam wanted him to run Lam, the Lam board of directors. So they bought OnTrack to get Bagley as the CEO. He brought in some other people, mostly from Applied Materials. And the single most important thing that he and his COO that he brought in, Steve Newberry, did was they created a set of core values for the company, things that you'd look at and say, well, yeah, like achievement is the first one, honesty and integrity. And everybody's like, yeah, you think I'm dishonest? What? That's almost insulting. Open communication, continuous improvement, innovation, teamwork, mutual trust and respect. And the one I think that's most important is think, customer, company, individual. And the idea was the customer's not always right. You don't always just do what the customer says. But when you're trying to make a decision, you should think first, what's the impact to the customer? What's the benefit to the customer? Then you should think about what's the impact to the company. And lastly, you think about what's the impact to the individual group or the individual person in the company. And I found that core value alone helped me make most of my big decisions throughout my career at the company. And they didn't stop there. They rolled this out. And people don't like me to use this term, but I will. They brainwashed us. For 5 years, Mr. Newberry would meet in group settings, first with the management, all the management in the company, then basically every employee. And we would talk about the meaning of every word and every core value and why those words were chosen and not other words. In other words, why think customer, company, individual? Why not think customer, company, and individual? Or then individual? That's the kind of discussion we would have. And so it became integral to everybody's being in the company, and people would call each other out. Well, you're not showing me mutual trust and respect. Open communication is really about being willing to tell the unvarnished truth, especially to your management, when they don't want to hear the bad news, or they're making a decision that you think is wrong. And that if you think that decision's wrong, you're not willing to just turn the other cheek and accept it. You escalate over your boss's head and you tell your boss, open communication, you're forcing me to escalate this because this is just the wrong decision. And they taught us you don't stop until you go to the chairman of the board if you think that a decision is wrong. And that made the whole company get aligned around the customer, the company's objectives from top to bottom, inside and out. And we just moved as one team. That's those core values and the way in which they were implemented, single most important reason for the turnaround of Lam Research, which was 1 quarter from bankruptcy in 1998. And today I think is approaching $400 billion in market cap.
So core values were a huge, important piece of this. Eventually, you obviously were on the technical side at Lam. You eventually rose to be the CTO, and you were very much the head of products as well. How do you make decisions? How do you prioritize your work? Because for Lam, technology is consequential, right? It's the way you win, or it's the way you don't win and you lose. So how do you make decisions to really be winning on the technology side?
Well, as head of products, I found it a lot easier than being chief technology officer, and I can come back to that and explain why. But the first thing is to be very closely tied to your customers and understand your customers' roadmaps, where they're going, and what their future needs will be. And we tried, not always successfully, but to the extent we could understand our customers' roadmaps and where they were going, because that would drive our customers' roadmaps. So you wanted to go look out as far as you can, and you look at those technology trends and you break it down and say, okay, where are there big gaps? Where are there's a need for a different solution? Because if you just are trying to beat out your competition who's already entrenched with basically the same solution, the customers are very resistant to change. The cost to change is huge. Requalifying a chip can take a year or more if you're in the automotive industry, for example, for reliability reasons. So that's a not a very good strategy. You have to look for what we call inflections, where the technology is going to change and there's no solution today. And there are many examples. One was we forecasted in 2003 that single patterning was going to reach end of life pretty soon. And we were laughed at, but we were right. So we started, if you're going to do multiple patterning, every time you do an imaging step, development, and etching, you're introducing variability that can end up in variability in the device performance. And that can affect yield and cost and so forth. So we focused on how to reduce variability in our machines such that when multiple patterning came in, we would have the lowest variability per step of anybody in the industry. Worked like a charm. Another example was NAND technology was planar two-dimensional devices. And it was very, very clear. Our customers are telling us that they can't scale much longer. The devices are too small and they can't trap enough electrons in that device. It just isn't enough space. So they got to go in the third dimension. And we looked at the papers. They were publishing papers. They were giving talks. And we were skeptical, but because it looked like it was going to be a lot more expensive to fabricate. But this is what our customers were telling us they were going to do. So we said, we better get with it. And it was 3D NAND, instead of being lithography driven, is all driven by deposition and etching. And about that time, we also merged with Novella Systems, which was a deposition company. So we had a leading position in deposition, leading position in etch, and we focused our teams on developing solutions for this 3D NAND architecture. We came out of it, and I think customers told us our competition wasn't taking them as seriously, didn't believe it was going to happen. So we got a little lucky, perhaps. But we came out of that and we captured 100% market share in every critical etch step, 100% market share in one of the most critical metal deposition steps, and 80% market share in the other critical deposition steps. And that gave Lam a huge spurt of growth. There are others. The lithography transition from chemically amplified resist to extreme ultraviolet resist. When you go from immersion 193 lithography to EUV, you got the resist doesn't scale. We looked at that. We saw that. We could see it. So we launched this is when I was CTO, we launched a program with 3 or 4 people to go dry deposit resist. Nobody was dry depositing resist, a metal organic resist, expose it in collaboration with ASML and IMEC, and we ended up dry developing it. We developed a whole new resist system that was much more capable than chemical amplified resist. The jury's still out on that one. Took a little longer than I projected to shareholders at the time. But I understand that it's really taking off now. And it's certainly, I'm convinced it's still the future resist, the resist system of the future. But that's another example of an inflection that you have to look ahead and see where it is and then direct your energies towards capitalizing on that inflection.
So it's really the concept of skate where the puck is going, right? So
absolutely.
Listen to your customers. They're telling you what they want. Understanding that and the trends where these inflection points are. I think you talked about also AI, and we can come back to that in the context of physical AI perhaps later, but AI is another driver that you saw.
Absolutely. Well, AI is an interesting one because when I first started work at Bell Labs, and I started to diagnose these plasmas, and I was making lots of measurements, doing what I thought was a pretty novel, clever laser spectroscopy measurement. We could map the motion of ions in the plasma as a function of position and time, space-time maps. I developed a method to measure electric fields. But I was frustrated because I couldn't model these things quantitatively. So I felt like I never fully understood it. It was like a beautiful painting, but I didn't really understand where that beauty was coming from. I had a colleague who referred to some of my papers as JLATs, which probably not politically correct, but which stood for Jesus. Look at that. Which I found rather insulting. So I started to invest in modeling and starting to learn the fundamental physics and developing numerical techniques and collaborating with others. But we could never model quantitatively to the precision, which is today sub-nanometer, that's required to make these devices. But I kept pushing on that rope, trying to develop these codes in collaboration with others. And in 2015, I think it was, we had an offsite strategic meeting, and our guest speaker was Jensen Huang of NVIDIA. And Jensen got up and he started to talk about, and a little background here, context. We used to talk about how the whole industry was driven by gaming, and all we were doing was spending all this money and all this time, and all we were doing is helping to make better and better video games, better and better video cards sold by ATI at the time, AMD now, or NVIDIA. Jensen gets up and he talks about how he took his graphic processors and started to work with Elon Musk at Tesla on self-driving automobiles. And they'd sensorize a car and they'd drive it around. They get massive amounts of data and they turn the crank. And that was the origin of self-driving cars. 2015, a lot of people didn't know about it. He shared that with us. And I'm sitting there like, holy cow, I've been barking up the wrong tree. We just need to go out and collect a lot of data and turn the crank. And we went out to dinner. We drank a lot of beer. We had a really great time. I love that guy. He's brilliant. And the next day I woke up with a headache, not just because I drank too much beer, but I realized I couldn't do what Tesla and NVIDIA were doing. Because to get one data point from a plasma etch, I got to take a piece of a wafer, cut it up, I put it in an etcher, I run a process. That doesn't take too long, maybe 10 minutes. Then I got to mount it and thin it and take and use an electron microscope to measure what I've got. And a day later, and several $1,000s, I have one data point. So it'll never work. But I realized, the pure physics approach would never work. The pure data approach would never work. So what we hit on is we need a hybrid approach where you've got physics built into your data models that ensure you're going to conserve energy, conserve momentum, that you don't have to ask a machine with lots of data to rediscover Newton's laws or the theory of relativity for that matter. You can build that into your machine learning algorithms. And that's what we went out and bought a company called Coventor, and we got them focused on developing software products that our engineers could use to help them do machine learning with a little bit of data. Favorite technique is Bayesian optimization, if you're familiar with that. So we could accelerate how fast we could develop recipes. And I believe that initiative, that wasn't a new product, but that enabled Lam to move faster in developing recipes for customers with new chemistries and new plasma reactors.
So when it comes to innovation within Lam, how did you think about that? And I think would love to understand, do you look internally to your team to do that, or is that external innovation? How do you see that?
Well, there's an old adage that there are always more smart people outside your company than inside your company. That's just a truism. That's true for countries and states as well. And so the challenge, and this is more of my CTO challenge, was how do we tap into all those smart people outside the company and get the smartest ones working for us? So we would look outside the company and identify other companies in the supply chain, maybe suppliers to us or partner. We always partner with our customers, partner with a peer company like ASML, partner with university groups, partner with national labs, where they had something unique to offer and were willing to collaborate. And you got to figure out up front, okay, who's going to own IP, who has the right to practice, get that stuff out of the way. And then you want to open up the kimono and keep nothing back, because you can't innovate together if you're keeping secrets. The other principle I always tried to pursue was to create a diverse team, people with very different experiences and backgrounds. Because if you have a bunch of people who all think the same way, you're not likely to innovate anything. The best innovations come when you bring very disparate ideas together. And again, that you're much better, you're able to do that by partnering people with outside your company than inside, because by definition, everybody inside your company has a lot in common, and you're subject to groupthink. So those were some of the principles I tried to follow with innovation. The other thing that I struggled with, and I talked to a lot of people about this, as a CTO, and I'm launching these projects that are very speculative, not unlike what SOSV does. How do I know if I'm being successful? If everything I work on transfers to the business units, that's a failure. I didn't set the bar high enough. If nothing we work on ever transfers into the business or creates a new business unit, that's also the wrong answer. So I don't know what the right number is. And of course, it depends what the impact will be. But what was important was to measure it. So everything we launched, we kept track of. And when we kept track of what we shelved, what we transferred. Sometimes we transferred things and it died on the vine. So that it was important to keep ourselves accountable. And a call out to a Harvard Business Review article that I read about this time, which was, "You need an innovation strategy." Look it up. It's worth reading. And one of the things I took out of that was they categorized speculative projects along two axes. One was business innovation, and the other was technological innovation. And I forget the labels of the four quadrants, but the one that was both technically innovative and business innovative was arguably the most disruptive, right? And the one that was incremental business innovation, incremental technical innovation, that's business as usual. The business units do that all the time. So when we look at these programs and decide what we wanted to do, we would plot it on that simple graph, and that would help us to make decisions about where we wanted to invest. And as CTO in a $20 billion company, my mission is to create new business opportunities that get measured in billions, not millions. So that tool, that construct helped us make some of those decisions.
Yeah. Okay, so shifting gears a bit to the topic of manufacturing. First, can you comment a little bit on the current state of the supply chain, how you're thinking about that? How do current geopolitics affect that, especially with respect to us here in the U.S.?
It's a big question. The first thing that comes to my mind when I think about the supply chain or where America needs to become stronger, or America and its allies, is in manufacturing. We don't manufacture enough. And I've lamented for many, many years the loss of the manufacturing of consumer electronics in particular. That began the exodus as far as I'm concerned. And it was the business philosophy at the time in the 70s and 80s and 90s that manufacturing was a dog business. Margins were low. It was hard work. Anybody could do it. Asia was more than happy to take it off America's hands. And so we moved everything offshore where it was cheaper, and they were more than willing to take it. The problem with that is manufacturing, and manufacturing well, is a problem-rich environment that drives innovation and drives competitiveness and is actually strategic. So if you look at it from a dollars and cents point of view, the right decision was to offshore it. If you view it as a strategic asset that allows your system offerings to be more competitive, more capable, more compelling, then you want control over your manufacturing. So I I believe we need to bring manufacturing, not just, I mean, we manufacture chips in this country, and appears to be making a very strong comeback, and TSMC is making very advanced chips, not the most advanced chips in Arizona. So we have chip manufacturing in this country, and it's getting stronger, and it's all moving in the right direction. Elon Musk talks about building terafab. I think it's great. But that's not enough. And DeepSeek is a really good case in point. When you look at the system level offering, like an AI large language model, DeepSeek managed to create something that was very competitive without the most advanced chips. Because at a system level, there's lots of ways to solve the problem. Having the most advanced chip, sure, that's a great asset. And you can get sloppy with your software if you have the most advanced chip. And if you don't care about power dissipation, the most advanced chip is an asset. But if you don't have access to the most advanced chip, it's not the end of the world. There are lots of ways in which you can innovate. So I love Chris Miller's book, Chip War. I recommend everybody read it. He got it largely right, but there's one major thing that I disagree with him on, and that is he said semiconductors the new oil, and he talks about how we have to get most advanced chip manufacturing back to the U.S. I do agree with that. I would think we should have the most advanced chips made in the United States, but I don't think it's the end of the world if we don't have that today or tomorrow. There are lots of other ways to innovate. What's more important is that we have, if not on U.S. soil, at least between us and our allies, access and control to the whole ecosystem for making system-level products, be they consumer products, be they automobiles, data centers, everything that goes into a data center, you name it. And I tip my hat to Elon Musk in this regard. I had the pleasure to get a tour of SpaceX a couple years ago, and I was amazed. Completely vertically integrated. They had rows and rows of CNC machines and 3D printers. They're making all the little components that go in the rocket engines. They make the engines. They make the fuselage. They make the satellites. And our tour guide was explaining how that's their philosophy. They want to make everything and control everything. And I said, but you don't make your own chips. And he just looked at me. This was 2 years ago, maybe 3. And he says, not yet, and smiled. And they're going to do it. So we need that as a country. We need the ecosystem, and we need centers of excellence like is created here in Newark and New York with hacks. I mean, that's the right idea. You got laboratories and engineers, and everybody's working together to build systems and all the things that go into the system. That's our future.
Yeah. So following up on that, what do you think is needed broadly so that we can regain leadership in innovation and manufacturing? I mean, I think you're saying hacks plays a role in that. What are some other pieces that we really need, and how do we get that to happen?
Well, I think we have the nucleus in the semiconductor space anyway, in that the top 5 companies making equipment that are used to make semiconductors are in the U.S. sphere of influence. They're ASML, which is based in the Netherlands, and actually they do a lot of, they build their lasers, they build a lot of their systems in the U.S., they do a lot of design in the U.S., so they're a U.S. company. Applied Materials, based in California, Lam Research, based in California, KLA, based in California, and Tokyo Electron, based in Japan. Those 5 companies account for more than 80% of the equipment used to make semiconductors worldwide. You can't make semiconductors without the equipment. So if you want to build more fabs, it'd be a lot harder if you didn't have control over the equipment. And then you have to look at the supply chain of the equipment. A lot of the critical components come out of Japan, Korea, and China. So I think you have to have control over that whole ecosystem, the whole supply chain from rare earths to the system level. So I'd like to see iPhones and iPads and everything else Apple makes made in the U.S. And we have to learn how to compete. and not just say we can't do it because China's so much cheaper. No, we have to find a way to compete. The equipment industry has been fighting off competitors in Asia for a long, long time, and sometimes they have unfair advantage.
I guess the point is we need manufacturing capabilities because we learn a lot from that. That translates back into the innovation layer. And so we need that whole ecosystem of manufacturing, the know-how we get from it, and we need to think about these. We need to think about it at a system level, and we also need to think about sort of leapfrogging. Instead of trying to copy and be me too and do it here, we need to bring innovation to actually advance us in new ways, which I think comes back to how you approached it at Lam.
Yeah, well, at some point you always want to leapfrog your competition, but sometimes you just need to catch up before you can leapfrog. But I don't think we have an innovation problem in the U.S. I think we have a manufacturing problem in the U.S. I've just had a wonderful day I've spent with SOSV and HACS and talked to a few of the portfolio companies. There's no shortage of innovation. I saw some things that I think are very, very promising that could be very disruptive to the industry. And my old company better watch out. It's not just China and Korea and everybody is susceptible to disruption. And I don't know, I think probably the oldest company is a brewery, not a high-tech company. And high-tech companies end up getting into trouble because another Harvard Business Review article, famous by Clay Christensen, about the innovator's dilemma, right? How does a company that's very successful continue to innovate? And one of the ways is what I described, is you look into the future, and then that team I talked about building, it started with a few people in dry resist. Well, we ended up creating essentially an independent business unit inside Lam Research that I was able to insulate from the day-to-day demands of the business. That's what successful companies have to keep doing, and then startups aren't encumbered by that. They have other encumbrances, but startups are a great innovative engine.
Okay, so I want to talk a little bit about something that I think you pioneered around the concept of the semiverse and digital twins, and what role do they play? Yeah. How does that impact what we can do? How does that help us in manufacturing and going faster?
Yeah, I'm a big believer in digital twins, but that's maybe saying like I believe in motherhood and apple pie, because I think it's a basic capability that everybody has to have. And I supported the Department of Commerce CHIPS Program Office decision when they created a Digital Twin Institute, which has now been shelved. I think that's a shame. But I view digital twin technology as like buying a ticket to play the game. It's not investing in digital twin technology per se is not going to enable us to leapfrog China in their ability to manufacture consumer electronics, or to beat TSMC at their own game of making semiconductors, because they're all investing in digital twin technology as well. Digital twin technology basically allows you to innovate in the virtual world at a fraction of the cost, a fraction of the time in the real world. But it's a digital twin. You need a real world counterpart. So if you build a digital twin of a semiconductor or consumer electronic manufacturing line, and you don't actually have the physical asset, that's just an uncalibrated model of marginal value. So to me, it's a necessity. If you're going to be a world leader in manufacturing of anything, I think, and with the technology that's enabled by semiconductors, that you can digitally twin these things, not from first principles, but hybrid models that combine physics and data in the right way. And that depends on what you're manufacturing. It's a ticket to the game. It gives you the right to play. It doesn't mean you're going to win. You got to be better at it than your competition.
Okay, so recently HACS launched a new initiative, a partnership with PPPL, and we're building a new site in Princeton. It will be called the HACS Plasma Forge. And the purpose of that is really to commercialize and innovate with plasma. And so I think the question I have, I've been myself learning a lot about this intersection of machine learning and materials, and how we can actually use some modeling, start to use some modeling, it's still nascent, to really inform which experimental space is worth looking at, right? Experiments are costly, they take time, which is money. And so how do you see interactions at the plasma level that we can actually start to model? Where are we in that? And do you see the new partnership and the role of PPPL being able to actually bring those pieces together to help us go faster?
Well, there's no question that Princeton Plasma Physics Lab is a world-class laboratory focused on plasma physics. Now, in the past, they've been mostly focused on energy solutions, particularly fusion, but in the process, they've developed core competency in plasma physics, plasma modeling, plasma diagnostics, and all those things are applicable to the low temperature plasmas that are typically used in not just semiconductor industry, but in a lot of other industries. For optical coatings, plasmas are used in the medical industry as surgical instruments, as sterilization techniques. And the physics is extraordinarily complex. In principle, you could write down all the equations, but it's like quantum mechanics. You can write down the Hamiltonian of the world, but you can't solve the equation. And even if you could solve the equations, which you can't, there are parameters that go in those equations, numbers that you don't know, that are very difficult to calculate for real world environments. So again, I come back to you need to understand the basic physics, and it'll get you it'll give you the qualitatively correct direction, but it's unlikely to be quantitatively accurate. So it's how you combine the fundamental physics with the machine learning technologies, and that's rapidly evolving. And it's the hybrid solutions that are clearly going to win. And those same approaches are being pursued for those people working on fusion. In fact, there's always been kind of a symbiotic relationship between the people working on fusion and the people working in plasma processing for semiconductors, because the fusion plasmas near the wall, which is where the big problem happens when the plasma becomes unconfined and blows through the wall. If you look at the physics of those conditions, it's very similar to what you find in a glow discharge etching silicon or silicon dioxide. So there's a lot of synergy. The techniques are transferable. The knowledge is transferable. I'd love to see PPPL get more involved in industrial applications of plasma, because I think they can add a lot of value.
Okay, final two questions. So I know you think that people have been saying Moore's Law is ending for now, I guess, apparently 30, 40 years. But, as you look into the future and the demands of physical AI and thinking about your idea of skate where the puck is going, like, what do you see as the innovations that we need to enable that?
That's a really good question. Moore's Law, the way I look at it, is it's not dying, it's just changing. And it's a lot more interesting and challenging now than it was in 1980, or even between 1980 and 2020, where it was dominated by just making everything smaller. When I look back on it, I was like, gee, that's really boring. I mean, I like to say that the challenges or the questions are exactly the same today in plasma etching as they were in 1980. It's about straight profiles, selectivity, and throughput by and large, and no defects. None of that's changed. The solutions have changed completely because of the changing dimensions. The solutions of yesterday aren't viable to be solutions of the future. So that's true going forward. We need more control over the energy of the ions, the angle of the ions, the control of neutrals versus ions, which neutrals, which ions. Those are really challenging problems. And I've already seen some innovative ideas that will be very disruptive in that space. And then when you fold in all the new materials and device architectures, there's no end of challenges. And now there are some new challenges, like, the latest devices are nanosheets, And nanosheets rely on an isotropic etch, not an anisotropic etch. So you need to etch underneath and free up this cantilevered channel material. And I had a former colleague of mine point out, one of the beauties in plasma etching is if you get a little schmutz, that's Yiddish for dirt, I think, on the surface, and you got this ion bombardment, it just kind of blows it off and you can etch cleanly. When you're etching isotropically and you're coming in underneath, if I got a little schmutz, there's nothing to remove it. So I had a customer tell me, I want you to bring the ions down, and then when they get into the nanostructure, I want you to turn them at right angles and come in this way. It's like, I don't know how to do that, but that's the same customer who challenged me years ago. We were struggling with selectivity of, I think, oxide etching to nitride, and the best anybody could do was like 4-1, and we got it up to 71. I want 30-1. Like, that's impossible. I took the message back to the team at Lam Research, and less than 6 months later, we had a 30-1 process. So I don't know, maybe somebody will figure out how to do that. That's the kind of challenge that we should all embrace instead of saying that's impossible.
Definitely. Okay, final question is, and you touched on this a bit, but you had a chance today to spend the day with us at HAX. And thinking about the future of HAX Plasma Forge, how do you specifically see the approach that we have with the hands-on engineering and the space and the ultimately partnership with PPPL? How do you see that accelerating the translation of innovation into commercial impact?
Well, I'm sitting here because you convinced me that this is the right approach when we first met. The thing that really intrigues me about the approach that HAX is taking, SOSV is taking, is they're not just looking at companies and, doing all the analysis and the due diligence and placing a bet and putting some money in. They actually roll up your sleeves. You maybe with some state money, but your own money, invest in laboratories and equipment and engineers who are assigned to work with the startups and help them get over the initial hump of actually making something. And I think that's very differentiated and absolutely the right approach. In the end, it's theory is theory and PowerPoint's PowerPoint. What really matters is, can I make something and can I hold it in my hands and does it work? And so you're not just investing financially, you're investing people's time, talent, and you've created a resource pool that is shared and leveraged. So strikes me as a very efficient and effective, both efficient and effective way to develop innovative new solutions to all kinds of problems that the world needs to have solved.
Awesome. Thank you. Well, thank you so much, Rick, for being here. I'm going to give a plug to the book that you're writing, only because you said the more people are expecting your book, then the more that will pressure you to get it done. Rick is writing a book, so look for that next year to be published, hopefully. Thanks so much for being here. Thank you, everyone. See you soon.
Thank you.
SOSV Deep Tech Live.